So I wanted to go over, um, this is kind of an aside actually, it's not part of your book, but the way I learned to deal with solubility using what are known as solubility curves. And curve implies that it's not straight, but these are actually straight line graphs. And what we do is take the log of the solubility product expression, and I just sort of broke down the math here for you so you can see this. Then you get the log of KSP, and then you have the log of a product. Um, oh, that's supposed to be a superscript there. And this log of the product then becomes the log of the lead ion concentration plus 2 times the log of bromide ion concentration. Now, the log of KSP just ends up being this. And then I rearrange this so that I have the lead ion concentration on one side, and then I have the KSP and the log of the bromide concentration on this side. So what we're going to do then is we're going to take the log of bromide as X and the log of lead as Y and graph it. And if you don't recognize this, right, this is just a straight line. This is Y, this is MX plus B. Just that they have negative values. So that means the slope will be negative and it'll have a negative intercept. And when you do that, I just took a few values to graph. You only need 2 for a straight line. And this is what you end up with. And so -3, -2.5, -1, this is increasing bromine concentration, so log bromide. And this is increasing lead concentration. So what this line represents is the line at which the solid concentration of bromide, with the solid is in equilibrium with the concentration of its ions, which would be this concentration of bromide in the log scale and this concentration of lead in the log scale. So if you wanted to know, for example, let me get to the next graph really quick. The line actually represents all combinations of ion concentrations that are a saturated solution. Okay, and then if you go below, like to this side of the line, this is unsaturated. And then above means supersaturated. So if you do have a problem and you're wondering if the ions are going to be soluble, then what you do is you calculate the log of the lead ion concentration and the log of bromide ion concentration. Let's say you plot it on here, and let's say it looks like that. Then you know you're supersaturated, and then what will happen is both ions will precipitate out of the solution. You'll basically have a precipitation of both ions, and then this concentration returns back to the solubility curve. Another way to think about this is the line where Q is equal to KSP. So it's all combinations of ions, right? They give you a number equal to the solubility constant right here. If you end up having your data points like your log of your lead and your log of your bromide, and it's somewhere underneath this curve, let's say it's right here, right? Then there's no precipitation that takes place. And so while this seems like maybe a little bit more work in some ways, it's definitely a foreign concept. If you're doing checking of ion concentrations repeatedly, let's say you're in a wastewater management situation, or the situation I learned it in was chemical oceanography and determining the ion concentrations in seawater. We relied a lot on solubility curves. And then there's also an interesting thing about the solubility curves. There's also a lot of competing ions for precipitation, like carbonate, hydroxide, number of different ways that metal ions can be precipitated out of a solution. And each metal ion would have its own curve because it would have a different intercept and would have a different slope as well.